Good morning, everyone from sunny Porto. I'm Barton Adebekyan from Institute of Astrophysics and Space Sciences in Portugal, and today I would like to speak to you about the chemical link between stars and their rocky planets. After the small introduction, I will present our last works that we have been doing with our colleagues, whose names you can see listed in these slides. So we know that stars and planets form together, more or less together, from the same molecular cloud. So, and then the new formed stars are surrounded by protoplanetary disks, and fraction of this disk material condense into the planets or planet-forming blocks, and the rest evolutionarily accretes to the stars within a few million years. So, in other words, stars and planets both grow from accretion of the same material from the protoplanetary or protostellar disks. Because of this common origin, it is commonly assumed that the composition of planet building blocks and composition of rocky planets should, to a first order, correlate with the composition of the stars or stellar atmospheric composition, especially for the refractory elements. Refractory elements are the elements that have high condensation temperature and condensate can be condensed at even close distances to the stars where the temperature in the disk is significantly high. But what we observe? And what is the composition of stars and planets? Usually, I will say a few words about the structure of stars and what we mean by saying composition of a star. So usually, the structure of the stars depends on the mass of the star, depends on the evolutionary stage of the stars, but I will say a few words about the typical interior structure of sun-like stars in the main sequence. So we have the core in the center of the stars, where you have the nuclear fusion, and then next to the core you have the radiative zone, where the energy coming from the core goes to the upper layers of the stars, and then we have the convective zone. Here I can show you. So then we have the convective zone, and after where the energy transforms through the convection of the material, movement of the material. The upper than convective zone, we have the photosphere of the stars, where we have it's something that we see when we are looking at the sun or other stars. So the light that we see coming from the sun or other stars mostly comes from the photospheres. Above photosphere, we have the corona, the chromosphere of the stars, and then corona, where we see sometimes the flares or different activity or sunspots or different active regions in the sun. And usually, when we derive the composition of the stars, it's the composition that we estimate for the photosphere of the stars, which is a very tiny region when compared to the total size, the size of the stars. And it is usually assumed that the composition in the photosphere should be a good proxy of the composition in the protostellar disk. And here on the bottom of the figure, you can see that the sun, or this is the composition of the sun. Sun is made of mostly hydrogen. Almost 74% of it is hydrogen. Then the second most abundant element is helium, which is around 24 point something percent. And then the rest, which is less than 1.5%, is metals. In astronomy, usually we call metals everything that is heavier than helium and hydrogen. While if you look at the composition of the Earth, it's mostly 32% of the Earth is iron. Then we have oxygen, about 29%, and we have silicon, which is 15%. So we can see that these compositions are completely different, and one could argue that the stars or planets formed from the same in the same disk don't have the same composition. However, if we compare some specific elemental ratios, in particular the elemental ratios of refractory elements with very similar condensation temperatures, like magnesium over silicon or iron over silicon, we can see that the composition in the sun, in the solar atmosphere, photosphere, and composition in most of the rocky bodies in our solar system, like except Mercury, have very similar abundance ratios. Also, if we compare the composition of the solar photosphere with the composition of very simple meteorites, we can see that there is a good agreement within more or less 10% in the composition of most of the non-volatile elements. Volatile elements are those which have a very low condensation temperature. So in principle, for some specific elements and elemental ratios, there is a good agreement between the composition of stars and their, at least the sun and the most of the planets, rocky planets in our solar system. The case of Mercury is a bit different because it has a significantly larger core when compared to or significantly larger amount of iron when compared to the rest of the rocky bodies in the solar system. And there are several explanations for that, and one of them is a giant impact that changed its composition, the size and the amount of the metal. And in general, how we derive compositions of stars and planets, let's say rocky planets. Usually, as I said, that we have the interiors of the stars and we have the photosphere, where the radiation coming from the interior of the stars produce the continuum light that we see from the stars. And in this photosphere, we have atoms of different elements, and then they absorb the light coming from the interiors of the stars. And when they absorb the light, in the spectrum, in the visible spectrum that we observe, you can see it here. Sorry, here you can see some absorption lines. And in principle, for a given atmosphere, physical conditions in the atmosphere, the same given temperature, given surface gravity of the star, the strength of the line will correspond to the number of atoms that absorb the light. So what we do, we usually measure the strength of some specific lines. We use some model of atmospheres. We use some information from atomic physics, and we convert this strength of the lines to number of atoms. And this way we can estimate the composition of different elements. And usually because we cannot know the absolute abundance of these elements, we assume that the number of atoms of hydrogen is 10 to 12, and then we estimate the composition of other elements relative to hydrogen. The way how the composition of planet is done is a bit different. And it's different also how we estimate the composition, for example, for the Earth. For Earth, we can have a direct measurement with using seismology. While for all the other planets, exoplanets, what we do is the following. We use the two main commonly used techniques of planet detection, the radial velocity method and the transiting method, to estimate the radius and mass of these planets. So basically, when you have a planet transiting in front of the star, it reduces the intensity or the flux of the star. So for a given size of the star, the amount of this reduction of the flux corresponds to the radius of the planet. In the same way, when the planet orbits around the stars, because of the gravitational pull, the star starts to move, and this movement is reflected in the spectra, or the shift of the spectral lines that we can measure from the ground, from Earth. This is called, as you know, Doppler shift. So the amount of this Doppler shift, or the radial velocity signal, will correspond to the mass of the planet. for a given mass of the star. So if we know the mass of the star, and if we know the mass of the planet, we can estimate the density of the planets, and using some models of interiors of planets, we can estimate, of course, also the composition. There are composition of these planets. There is degeneracy because different compositions can give the same density of the stars, but you can always have a probability distribution functions of different compounds. So in the past, there have been many works trying to see whether there is a chemical link between stars and their rocky planets, and all these work give very important results. However, mostly because of the size of the samples, these previous works didn't allow to give to reach to a firm conclusion about this chemical link. So what we tried to do here, I mentioned a few works from Santos et al., Plotnikov and Valencia and Schulze et al. The last two papers have been published very recently, and there is no need to explain these figures, but these figures come from the works that are cited. Okay, so we try to fill this gap and to understand whether there is a link between the chemical composition of planets, rocky planets, and their host stars. So what we did from the different archives, we selected all the planets that have a good characterization of their mass and planets, between 20 or 30% precision in mass and radius, and we gathered spectra, high-resolution spectra for the host stars for all of them, the host stars of all of them. And here I show the radius mass diagram of these planets that are less massive than 10 mass of the Earth, and that are precisely characterized. You can see that there are two groups of planets: those that are marked in red, and those that are in blue. And there is a gap between the two. This so-called radius valley separates the potentially rocky planets that have smaller radius radii, and the planets that have larger radii. And this is because these planets most probably have volatile layers, or because they have atmospheres. So we decided to focus only on 21 planets that have well-characterized mass and radius, and that can be potentially rocky. And in the yellow line, yellow curve also shows the Earth-like composition curve. So basically, it shows what would be the radius of a planet for a given mass if it has the same composition as the Earth. And this curve is from the paper of Caroline Dorn and collaborators from 2017. So for this planet, using the models of Caroline, we could estimate the composition, and in particular the fraction of iron, the iron mass fraction relative to the other elements. And for the host stars, what we did is we derived homogeneously, we derived the composition of carbon, oxygen, silicon, magnesium, and also iron. These are the main major rock-forming elements, and they are most relevant to control the species expected for the equilibrium condensation models. So, for example, we use the simple stoichiometric equations presented in Santos et al. 2015 and 17 to estimate the fraction of iron relative to the fraction of other mass fraction of other elements. So, what we assume, for example, in these stoichiometric relations is that, for example, oxygen can be only in the form of water, and magnesium silicates like pyroxene or olivine. And we made similar assumptions for the other elements. For the other element, yes. Okay, so we have the chemical composition of the host stars, and from this coming from the photosphere of the host stars, and we assume that this composition is similar to the composition of the protoplanetary disk, And using this stoichiometric equation, we can estimate the iron mass fraction in the protoplanetary disks or iron mass fraction of the building blocks of planets. And from the previous graph, I showed that we had also the iron mass fraction for for these planets, and we can go to the next step to see whether there is a correlation between the two. And the next question is which approach to use. In principle, there are two main approaches when trying to see whether the composition of the planets and their host stars is similar or not. One way is just to compare individually the stars and planets, let's say their iron mass fraction, and the other way is to look all the system in one graph to see whether there is a correlation between the properties of planets or composition of the planets and composition of the host stars. Here I illustrate the main differences between the two. Let's assume that we are comparing the composition iron mass fraction in planets and their host stars. And let's assume that the error bar, the uncertainties in the composition of planets is significantly large. In the top plot, top figures, I show cases where the composition of the iron mass fraction of the planets and host stars agree within 1 sigma. So what we would conclude, looking at the top left figure, that the planet and their host stars have similar composition within 1 sigma. However, if we try to make a linear regression, this is a very simple case, we have, let's say, 3 points, we will say that indeed there is correlation, but this correlation is not significant. There is a 32% probability that this correlation comes by chance because of the large error bars. And in the bottom panel, I show a case where the error bars are smaller and the agreement is within 3 sigma. Most probably, we would conclude that the stars and planet have different composition within 3 sigma rather than they have similar composition at 3 sigma level. However, if we look at the correlation between the two, we will see that there is a significant correlation. The probability that this correlation is by chance is only 2%. So basically, when you are looking for correlation, your results are more sensitive to the uncertainties. And in our opinion, this is the way to go, and we decided to follow this approach. So next, what we did, and what is shown in this plot, is the comparison between the iron mass fraction in the planets as a function of iron mass fraction in stars. So on the x-axis, you see the iron mass fraction of stars, and on the y-axis, you see the iron mass fraction of planets. And there are two figures. On the left figure, we assume that the iron in planets is only in the core, and on the right plot, we assume that the iron can be both in the core of the planets, also in the mantle. So this gives slightly higher iron mass. In the second case, we have a bit more iron mass fraction than compared to the first option. Anyway, so in both cases, we see that there is a very good correlation between the two, between the iron mass fraction of planets and their host stars. So this is a very good evidence that the composition of planet is linked to the composition of the planet building blocks as inferred from the host star atmospheres. However, you can also see that the correlation is not one-to-one. So in general, the iron mass fraction in planets is a bit higher than the iron mass fraction in the planet building blocks. So it was recently suggested that the planets that are formed close to the rock lines, so this is the region where the refractory material can condensate and sublimate. So when the planets form close to these rock lines, the iron fraction in planets can be significantly increased due to the recondensation of already evaporated pebbles. Pebbles are millimeter-sized cluster of rocks, so that are used to form planets. So this was proposed in Agushin et al. And collaborators in 2020. And if this process described by these authors is true, then the fact that there is a correlation between iron mass fraction of planets and the host star iron mass fraction suggests that the process described by these authors is a function of the initial composition of the stars. So the higher the iron mass fraction in the protoplanetary disk, higher the effect described by Agushin. So the higher will be the composition of the host stars. So if one wonders whether the correlation that I described here is significant or not, I can assure you that they are significant. We tried many different tests using frequentist and Bayesian approaches, and also using several Monte Carlo tests to see whether the result could be by chance, because the sample is relatively small, only 21 planets. But all the results show that the correlation is significant, at least at 3 sigma level. If you can have a look, I mean, zoom in perhaps the table to see the values, or you can wait until the paper is accepted and is published to look to more details. So in conclusion, I can say that the rocky planet composition should depend on the chemical composition of the protoplanetary disk where they are formed, and it contains a lot of information and signatures about the planet formation processes. Generalizing it a bit and linking to the habitability of the planets, about which we will see more in the next talks, we can say that most probably, if the habitability is linked to the composition of the planets, it also links to the composition of the host stars. So all these criteria for the habitability perhaps should be looked together with the properties and the composition of the stars and their planets. This is my last slide. Thank you.
Thanks to Barden for the great overview on stellar abundances and how to use them to better understand the composition of their planets. So for this segment of the talk, I'm going to be taking it a step further to show how element abundances and the biogeosciences can come together to take a critical step towards detecting life on exoplanets. This work cannot have been done without my esteemed colleagues, Hilary Hartnett and Patrick Young, both of whom are at Arizona State University. So to begin, we understand that habitability is extremely complicated. It's not enough to say that a planet has liquid surface water, or even that it's within the habitable zone, or the distance such that the planet would have just the right temperature such that if there was water on the planet, you would get liquid surface water. This is not enough of a criteria in order to define exoplanet habitability. Instead, I really like this figure that Rory Barnes and Vicki Meadows put together in 2018. This is sort of lovingly called the planets are hard diagram, because it really shows all of the complicated aspects of exoplanets and all the different properties that we absolutely have to know in order to define whether or not these planets might be habitable. So on the left side are the stellar effects. So this is like the galactic location, composition, and structure, which my little picture is covering up, but we'll get to in a second. As well as the spectral energy distribution. So what kind of radiation does the star put out? Then on the top right, we have all the influences from the planetary system itself. So not only about the orbital evolution of the planet we're interested in, but whether or not there are other planets within the system which can really impact the planet that we are considering. And then, of course, you have all of the properties of the planet that we're looking at: the orbital dynamics, the surface, the atmosphere, as well as the interior. So all of these properties are absolutely vital to determine overall holistic planetary habitability. And by that, I mean, it's not enough to say that a planet, like I said, is in the habitable zone, or even that it has one Earth mass and one Earth radius, or that it has oxygen in the atmosphere. We need to know quite a lot more about the system in order to really, truly say that a planet could be habitable. So for today's portion of the talk, I'm actually going to be focusing on how to go from the composition of the star, which you can now see in your on your screen. So the metallicity and the isotopic abundances, and what that means for the interior of the planet as well as the surface of the planet, what and all the different elements that could be available for biology. And this is drawing upon what Varden already discussed, which is that stars and planets are formed at the same time and from the same materials. Therefore, we can sort of take roughly what's in the star and use it as a proxy for the composition of the planet. And this is really a sort of a necessary step right now. Of course, it's not perfect. There's still a lot of work to be done, but it's a necessary step because it is not currently possible at the moment to determine the interior composition or even the surface composition of an exoplanet. We don't have that technology. It doesn't exist. So right now, the best thing we have is to use the host star elemental abundances as a proxy for the composition of the planet. So let's take a step back here and let's talk a bit about photosynthesis. Which I know is a bit of a jump, but bear with me for a second. So, in order for to create life, we have to have a very specific sort of recipe to create life as we know it. So, of course, this is all assuming that it's kind of Earth-based life, or the only data point of life that we have, and you have to have elements that are brought together in very specific molar ratios, such that these certain reactions can happen. So what you're seeing on your screen right now is the equation for photosynthesis, and the numbers that I've highlighted is that you need essentially 106 carbon atoms, 16 nitrogen atoms, and 1 phosphorus atom. So this is the recipe that we need in order to create life. And so the second part of that equation, what we're seeing is the 106 to 16 to 1 creates biomatter. That's that first expression. In addition to the biomatter, we also get oxygen, and I will come back to that a little bit later. But the key thing to take away here is that you need, for this recipe, you have to have 106 to 16 to 1. This is crucial. So it's very similar to like baking a cake. If the recipe calls for 4 eggs and you only have 3, then that cake is going to be really gross. So in order to have a habitable planet, you need to have an edible cake, and that means having the recipe just as we see it. Now, the only issue with this is that phosphorus, which is typically sourced from phosphate, is actually fairly difficult to get a hold of. It occurs by rock weathering, and it tends to be the limiting reagent for life. So this is sort of the hard part. This is the crux of the photosynthesis equation. But like I said before, we can't measure the surface composition of an exoplanet yet. So instead, what my collaborators and I did is that we can use the stellar abundances of carbon, nitrogen, and phosphorus in order to understand those relative abundances within the stars and understand their availability, therefore, in their exoplanet interiors and the planetary surface. So in order to do this, we use the Hypatia catalog. This is a database that I put together a number of years ago. It's the largest database of stellar abundances for stars that are relatively near to the sun. And what I mean by that is that all of these stars are, so these are F, G, K, or M-type stars, all main sequence stars, so have a long time to live, fairly stable, easy to measure their elemental abundances, all of them within 500 parsecs of the sun. So in total, there are 9,434 stars currently within the Hypatia catalog. This database was put together by amalgamating about 215 different literature sources in order to create a largest database as possible. Currently, the Hypatia catalog has 77 different elemental abundances. So, like I said, this is something that I've worked on for a long time, and it has even a front-facing website such that anybody can access the data. So this is really what we use because it's quite a big resource with all of the different elemental abundances. The Hypatia catalog is one of the few multidimensional databases in the community because I've combined elemental abundances for stars as measured by a variety of different teams. So I put that together, and in total, there are about 350,000 different unique elemental abundance measurements within Hypatia, which you can access at hypatiacatalog.com. Now, because everybody always mentions, I like to explain that the Hypatia catalog was named after one of the first known female astronomers. She was very well respected in her time, which was about 400 AD. She lived in Alexandria. And yeah, she was a very strong, independent woman, somebody that I very deeply respect. And so I wanted to show that respect by naming my database after her. Anyway, I've sidetracked, so coming back to the elemental abundances. So Varden sort of talked to you already about how we measure these different elemental abundances. So what you're looking at here is sort of a standard astronomer's plot where you have phosphorus with respect to iron on the y-axis, and on the x-axis is iron. The reason that we do this is because iron kind of acts as a chronometer. There was no iron at the beginning of the universe. It has been slowly created within the interiors of stars and then exploded outward to the rest of the universe. So, and because of the different nucleosynthetic origins of iron, it's been basically monotonically increasing in time. So by having iron on the x-axis, we can sort of consider it to be a chronometer as a way to understand different how these different elements have changed with time with respect to iron. So this is all sort of a variety of different kinds of normalizations. So this is a fairly standard astronomer's plot. All the stars that you're seeing are the about 100 stars within the Hypatia catalog that have phosphorus abundances. All of these different stars have been color coded to show the different distances, just to get a feel for the variety of regions that we're looking at within the galaxy, because different the stellar abundances of disk stars might be different than, or are usually different than, the stellar abundances from thick disk stars or the galactic halo. So what we're seeing here is that the majority of stars have iron and phosphorus abundances that are relatively close to zero. Zero in this case is going to be the sun. All of these elemental abundances are normalized to the sun. But then you have a variety that are actually rather iron poor, so you're in the negative part of the iron, but some of those are iron poor, but they're phosphorus rich with respect to the sun, which is fairly interesting, although some of them are both iron poor and phosphorus poor. So this is generally the sample that we see with when we're looking at the different phosphorus measurements for all known stars with phosphorus measurements. This is it. I poured through all the different data sets to try to find phosphorus measurements, and this is as many as we have. This is it. So remember, the Hypatia catalog has about 9,500 stars, and yet only 100 have phosphorus measurements. So that is something we will come back to. All right, so moving on. So now we're going to sort of take a stab at the C to N to P ratio. This is also called the Redfield ratio, which has been around since the 30s because it was discovered that almost all life within the Earth roughly follows this 106 carbon to 16 nitrogen to 1 phosphorus. So here we're looking at a slightly tweaked version where instead of looking at phosphorus, we're looking at carbon, nitrogen, and silicon. So we included silicon because it is still very important to life on Earth, but also because there's quite a lot of silicon abundances, as you can see. So here we're looking at about 2,800 stars, about 1,000 of which are exoplanet host stars, which you can see as the black triangles. And so, yeah, so about these 2,800 stars all have C, N, and Si abundance ratio. So as indicated by the histograms on the X and Y axes, the majority of the stars have C, carbon to silicon molar ratios. So taking a step back, we're now looking at molar ratios, not abundances anymore. So these are no longer with respect to the sun. They're no longer normalized to the sun. Now we're just looking at the pure molar terms. Okay, so the majority of stars have carbon to silicon molar ratios that fall within about 5 to 10, as you can see with the histograms, and the nitrogen to silicon all fall between like about 1 and 3. In comparison, the majority of exoplanet host stars, like I said, those are the ones with the black triangle, span a smaller range, especially with respect to nitrogen to silicon. Then looking at the distribution of planets in our sample, we found that the planet population is fairly random, varying from smaller Earth-sized planets to mini Neptunes and then Jupiter-sized planets. So it's running sort of the whole gamut of different kinds of planet sizes. What you can see also is that we've overlaid the molar ratios that we expect to find within the Sun, bulk silicate Mars, bark silicate Earth, Earth's crust, and as well as plankton. Plankton you can kind of see in the middle as that little clover leaf. All right, so that's carbon, nitrogen, and silicon. So let's take some slightly different versions. So on the left, what you're seeing is phosphorus to silicon with respect to nitrogen to silicon. So there's only 54 stars that have all three of these abundances measured for them, 12 of which are the exoplanet host stars. There aren't really any obvious trends in either population, although most stars have phosphorus to silicon between 0.007 and 0.011, while the majority have nitrogen to silicon between 1 and 2.5. On the right, you're looking at 93 stars that have carbon, phosphorus, and silicon all measured, where 16 of them are the exoplanet host stars. The general trend for the majority of the stars is that increasing silicon to carbon is accompanied by a proportionate change in phosphorus to carbon, as well as vice versa. So this is likely indicative of different production sites for the elements, since phosphorus is primarily produced in massive stars, where carbon is created in asymptotic giant branch stars. So these are stars that are leaving the main sequence and are sort of in their final death throes. While silicon is made in massive stars with in type 1a supernova. So very different nucleosynthetic production sites, which is likely why we're seeing the sort of increasing trend between silicon to carbon and phosphorus to carbon molar ratios. All right, so a little bit of trends with respect to these elements. So now let's look at the final sort of ultimate plot that we're really here for, and this is that C to N to P plot. Now, we've broken it up into two different scales in order to get a better sense of what we're looking at here. So the plot that's kind of like in the background is has nitrogen to carbon on the y-axis, but on the x-axis, you're looking at phosphorus to carbon for the entire scale of everything that we're considering here. So that's not just the stars, which actually occupy a fairly small section of the phosphorus to carbon molar ratio range, but you can see how much these different ratios are vary, especially with respect to solar system planets. So you can see with the brown O plus is that that's the bulk silicate Earth, and then you have the upside down U, which is Earth's crust, which are fairly phosphorus rich. Compared to the other stars. And then you have Mars, which is all the way on the other side. We had to like really stretch the scale in order to show bulk silicate Mars. So it's clear from the literature that it's difficult to measure phosphorus within stars. We're only looking at 54 stars here, so it's not even all the phosphorus, but to have a star that measures phosphorus, carbon, and nitrogen within it, clearly it's a difficult thing. So we're only looking at 50 stars, and so that makes it difficult to outline plausible ranges and generalizations for phosphorus abundances within nearby stars, especially those stars that have exoplanets orbiting them. However, the interesting thing that we noted while looking at all these different kinds of plots is that the sun might not be sort of a typical star in terms of its composition. I mean, yes, it's the only one around which we have confirmed life. That is us. However, it's been quite varying when we've had these different plots. So we know that the specific molar ratios of C to O and Mg and magnesium to silicon are more conducive to habitable planets than others. Namely, we tend to look at C to O ratios that are less than 0.8, because C to O ratios that are above 0.8 to about like 1 are likely to produce geodynamically inactive planets. However, phosphorus is absolutely required for life. So this ultimately places a lower bound on what is necessary in the star to go from the star to a planet to life. For example, if there's very little phosphorus in the stellar birth cloud, then there won't be much to add as a planetary veneer, which is absolutely critical to life as we know it on Earth. Because what little phosphorus may be available could be subducted into the core, as is what happened with the Earth, with only insignificant amounts available to escape onto the planet's surface. So while we know that there are a variety of very key and important elements that are necessary for building planets, so carbon, oxygen, magnesium, and silicon, phosphorus is absolutely crucial to life, and so that it must be sort of taken into account when discussing overall habitability. And so again, we don't have a lot of data here, but we might be able to place sort of a lower bound in order to move forward to try to find more habitable planets. So sort of taking this all together, then this is a breakdown of what the different C to N to P ratios that we expect to see. So you can see the plankton, Earth's crust, bulk silicate Earth, bulk silicate Mars, which is what we showed on all of those different plots. But then you also see the sun as well as nearby stars. So so the nearby stars is not just all the stars that we showed. We actually took the average value for all of the stars within the Hypatia catalog to get a general sense of what the C to N and P ratio is going to be just in a normal star. So not just those stars that have phosphorus in it. So the sun actually appears to have a C to N ratio that's fairly similar to the Hypatia average. However, the sun has carbon to phosphorus and nitrogen to phosphorus ratios that are a factor of 2 lower than the Hypatia average, which strongly suggests that the sun is relatively phosphorus rich, which is really interesting. And while individual stars may have larger error bars, there's no reason to believe that the entire sample is systematically shifted, such that the position of the main locus of the stars relative to the sun should be sufficiently accurate to confidently say that the sun is unusual, especially with respect to phosphorus, which is something that we really need to take into account. Earth and Mars ratios indicate that they are fairly nitrogen poor and phosphorus rich relative to the sun and to Hypatia stars. One hypothesis is that nitrogen, especially since it's a volatile element, is preferentially segregated towards gas giants, while phosphorus, which is more of a siderophile or tends to love iron or be attracted to iron, is thought to be condensed into the cores of rocky planets. So this really sort of summarizes the point that it's likely that stars that host planets are going to need, especially rocky planets, are going to need a decent amount of phosphorus in order for the phosphorus to continue to not just the planet's core, but also to become a thin veneer on its surface. Now, this is very crucial to understand, because when it comes down to it, ultimately what we want to do is to find signs of life. Now, I showed you that photosynthesis equation earlier, and so we took the 106 to 1 carbon to nitrogen to phosphorus, we put it together, and not only did we get biomass, so life, but we got this signature of oxygen. Now, a lot of people are looking for different kinds of signs of life as a way to see or try to confirm that there's life on other planets. However, what they've really been looking at is this oxygen signature sometimes in conjunction with other types of signatures, methane, ethane, things like that. However, we have to be very careful when doing this, because not only could this oxygen signature come from life, but it could also come from important geochemical processes that are occurring on the planet. So ultimately, we have to understand what the net planetary biological production is, such that we can remove all of the influences from the geochemistry on the planet in order to really assess that these signatures came from life. So we need to be able to say that this net planetary biological production is much, much greater than 0 once we account for the fact for these different biogeochemical cycles that occur. So the planet's composition dictates both its geochemistry as well as its biochemistry. And this is absolutely critical to understand because there are huge number of different elements that are absolutely important for understanding life. For example, not only so you still saw this plot earlier, which is what I showed you with the Hypatia catalog, but now it's color coded to show all of those elements that are important for rock and planet forming, those elements that are important for life, and since blue plus yellow equals green, those that are account for both. Now I've highlighted a few of those elements. That's nitrogen, fluorine, phosphorus, chlorine, and potassium, and you'll notice that we have a dearth of measurements for these specific elements within FGK and M-type stars. And part of the reason is because these lines are not very strong in the optical band, which is where a lot of the astronomical observations tend to happen. So we have to look for them in other places. And that's difficult to do. It requires whole different kinds of new kinds of instrumentation and technology in order to be able to go after these specific elements. However, these elements are crucial. We need to be able to understand them, what they look like within these different stars, and therefore their planets, and therefore life. And so it's important to go after these specific elements that are crucial for planets and life. So I actually call these interdisciplinary elements because they have reasonings behind them, why we should go after them that extend beyond astrophysics and spectroscopy in order to better understand overall habitability. So the reason for this is because, like I said, and like Varden said, going from stars to planets is actually really complicated, but it can be so important for our understanding of planets. So as a quick demonstration, here we're looking at an artist rendition. So these are not photos of the TRAPPIST-1 system. So this is a fairly popular system among astronomers because it has 7 detected planets in a very small system. In fact, you can see the comparisons between TRAPPIST-1 and our solar system. And TRAPPIST-1 is a small star. It's an M8 star, so it's very dim, it's very small. And in fact, the comparison in the solar system is actually better to compare it to the moons of Jupiter, which you can't really see because I'm in front of it, but rather than the solar system itself. Now, people are really excited about this system because there are 3 planets that are within the habitable zone. So this is at the distance from the star at which, if there's water on the surface, that it's likely to be liquid. So planets E, F, and G are within this habitable zone. However, what my collaborators and I did, so this is a different set of collaborators. This is a paper led by Cayman Unterborn. What we ended up doing is taking the elemental abundances of the star, putting them into a mass radius thermodynamic calculator, and determined the overall planetary interior structure of these planets. So rather than sort of looking like an Earth-like planet, we found that these planets have a huge amount of water. TRAPPIST-1c has 8 weight percent water, which is what you can see on the left. So this is a phase diagram, which is essentially like a stretched out pie chart. So you can see that 100% of the core is liquid iron, and then different kind of perovskites, and then you can see the different kinds of ices with respect to the depth. So TRAPPIST-1c has 8 weight percent water. TRAPPIST-1f has 50 weight percent water, and in comparison, the Earth is 0.02 weight percent water. So it's a huge difference. It's huge. So understanding what's available on the surface actually is incredibly powerful because here we have a lot of water that's on the surfaces of these planets. And in comparison, the Earth's crust has a huge variety of different kinds of elements. It's not just water, it's a lot of other things. But the fact that these TRAPPIST-1 planets have so much water actually means that even if there was life, it would be really difficult to find it because ultimately planets need to be alive. These planets need to have cycles. They need to be churning and moving different kinds of these various elements around. What you're seeing here is the carbon silicate cycle, where CO2 is dissolved in rainwater, which is a weak acid that weathers silicate rocks. The dissolved minerals are carried by the water to the ocean, which are used by living organisms as shells. Eventually, the shells are buried in the seafloor to be subducted and then combined with silicate via volcanism. And then it goes back in the atmosphere, and the whole thing starts again. So on Earth, this is a very important cycle that's critical for moving around these different kinds of elements. But by having that huge amount of water on the top of TRAPPIST-1, it means that not only it means really that you have very limited geochemical cycles that could occur on these planets. And that's a really big deal, because we absolutely need to have planets that are moving, that are alive, that are able to keep renewing the different resources within them. And so ultimately, we realize that the climate, the mantle, and the core are all coupled together, especially with respect to rocky planets. And so you have like the different atmosphere and climate, and that's linked to the tectonics, and then eventually the magnetic field. And so you have all these things that sort of interact with one another. So I'm going to end it there, because actually Guillaume is going to be talking to you about magnetic field in a lot more detail. So I'll leave it to him to discuss that role in a lot more detail than I am able to get into. So with that, I'd like to thank you. If you want to access the Hypatia catalog or get in touch with me, this is my contact information. So thank you very much.
Thank you, Natalie. Thank you, Vardon. I am Guillaume Gronoff from NASA Langley Research Center. I'm going to present to you our work on the atmospheric escape processes, work that was done with the Living Breathing Planet, a group that was funded by the NASA Nexus for Exoplanetary System Science. Work that involved a lot of people, as you can see here, and that is linked to the big question of planetary habitability in a very interesting way. First, we have to consider what are atmosphere. Atmosphere has a link between the planet, the stars, and the observer. We have seen that the composition of the star is linked with the composition of the planet. However, that planet composition is not homogeneous, because the light elements have a tendency to go up, and they can escape from the solid part of the planet and create the atmosphere. Understanding the composition of the atmosphere is really necessary to see if the planet is going to be habitable or not. But however, we have to understand that not all the atmosphere can sustain liquid water or conditions that are really susceptible to host life. And a big point that we have to understand is really the atmosphere evolution. Let's look at the solar system's atmosphere. We see that Mars and Venus are CO2-rich atmospheres, while the Earth is a N2O2 rich, and it's what we call habitable. But what about Titan and its N2 rich atmosphere? Habitability, as previously said, it's a very confusing concept. And in the rest of this talk, we are going to really concentrate on these planets that are able to sustain liquid water on their surface. So is it possible to detect habitable worlds around other stars and to characterize them? When we work with the GWST, it's a problem, because for reason of signal to noise ratio, we will only be able to characterize the atmosphere of exoplanet around M dwarf. So it's not to say that we cannot do other kind of exoplanetary work with the GWST, but if we want to be able to have a good idea of the atmospheric composition around planets that could be able to host life and host liquid water, then the main target are M dwarf. However, all the exoplanets that are in the habitable zone of M dwarf are subject to really high AUV XUV fluxes, so extreme UV XUV fluxes. And there is a lot of problem of what these fluxes can have on the atmosphere. And people have been wondering if it could be fine if the atmosphere is shielded with a magnetic field. However, there's a lot of questions there, and we are going to try to understand them more and solve them. So we have to be very careful when we are speaking about the atmosphere, because atmosphere are not a static thing. Atmosphere are basically the result of an equilibrium that can be in a very short period of time between the different processes shown in this figure. The main processes we have to take into account are the outgassing from the planet and the escape of the atmosphere into space. We have a little bit of exchanges in condensation and fixation to the ground or the ocean and evaporation, and we have also to consider the meteorite and the initial accretion that can bring to the atmosphere. However, that extremely active chemistry is seen only in special cases, and the Earth is a beautiful example of that dynamics. For other planets, really outgassing and escape are the main processes. For understanding an atmosphere of a possible habitable zone planet, it's extremely important to see to look at the escape and at the outgassing. And the escape is something extremely complex to understand, as I will show in the following. One of the very interesting things is that we have also the notion of exobase, when the scale height is equal to the mean free path of the molecule. That means that it's basically unlikely for a molecule of the upper atmosphere to encounter a collision when it tries to escape. To better understand what are the escape processes, it is necessary to understand what is the upper atmosphere. When I speak about upper atmosphere, I speak about the thermosphere and the ionosphere. At Earth, they happen at 100 km altitude, which corresponds basically to the limit of space. A fun fact is to realize that the aurora, the northern or southern light, happen in the upper atmosphere because they are generally above 100 to 200 km altitude. Two notions are very important to know over there: the notion of scale height and the notion of exobase. The scale height, basically kT divided by mg, is what would be the height of the atmosphere if it had the same pressure everywhere. And when we speak here, we generally speak about the scale height of the atmosphere above us, so it can vary a lot from the scale height that we have at the ground. The second important notion is the exobase. It's basically when the altitude where the scale height is equals to the mean free path of the atoms or molecule. And that exobase, what it means is that an atom of molecules is extremely likely to encounter no collision when it starts to escape. And the higher you go above the exobase, the less likely a molecule that has a good speed will be prevented to escape the atmosphere by collisions. The main parameter influencing the conditions in the upper atmosphere, conditions like the temperature, density, scale height, are basically the atmospheric composition and the presence of solar or stellar AUV, XUV, as well as the particles and the field. It's important to take into account the chemistry because it changes the composition, the heating and the cooling, the radiative processes that cools or heat up, and also processes of the diffusion of particles, conduction of temperature, winds, etc., etc. In this little sketch, you can really see some of the important parameters from the sun and where they affect the atmosphere. And one of the very interesting things is the influence of the solar activity on the temperature in the upper atmosphere. You can see that the temperature at the exobase above 500 km can really change from 500, 600 Kelvin to more than 1200 Kelvin. And that really affects the escape processes. So how to study the upper atmosphere? First, it's very important to have models to be able to really understand what is going on in the thermosphere and the ionosphere, which can be in one dimension, which is really helpful to work in a lot of very different ways and to study all the whole parameter space. But then we need to work for being more precise with 3D models. It's also very important to be able to have the model of the solar wind, solar radiation, and particle acceleration, because these models are working as inputs to our work. However, it's also very important to have laboratory experiments to be able to have the input parameter for these models. And finally, what would be a model without something to validate it with? And satellite observations are really necessary to validate our model. The SABRE mission, Mars Express, Venus Express, Maven mission really helped understanding all these escape processes. And there are several other missions, of course, that work on this subject. So first of all, let's speak about the different escape processes that exist at planets and exoplanets. It was one of the very first things we did with in our work is to really make a review of all that exist, because processes that are negligible now could have been non-negligible in the past or could not be negligible at exoplanets because they are subject to different conditions. Let's explore the different escape processes. In this figure, you see that we have two main sources of energy that will lead to the escape of atmosphere: the stellar wind and the stellar EUV XUV flux. And we have two main cases and a case that is basically in between. We have the case of unmagnetized planet, the case of magnetized planet, and the case of both, because some processes do not have a problem with the magnetic field. When we speak about all the planets, we have the question of the photochemical escape and the question of the thermal escape that happen everywhere. When we speak about the magnetized planets, we have very specific escape processes such as the ionospheric outflow. And when we speak about unmagnetized planets, we have exchange with the solar wind, solar stellar wind, and we have pickup and sputtering processes. And then we will see that all these processes are of importance in their really specific cases. Let's speak about the thermal escape. We have two kinds of thermal escape: the slow thermal escape and the fast thermal escape. When we look at the Maxwellian distribution of the species in the upper atmosphere, for example here, hydrogen at an Earth-like planet, we can see that the distribution of the species in function of the temperature means that there is a tail in the distribution that is above the escaping speed. And when we are at the exobase, basically there is only it's extremely lucky for a species going up at that escaping speed to be lost into space. So if it's only a small part of that tail that is escaping, it will not change the Maxwellian distribution in big ways, and basically we can make the approximation that we are at a certain temperature and that we still have a Maxwellian, and that's what we call the Jeans escape. However, if a large part of that tail is above the escape speed, then we have a problem. We cannot really approximate the escape like we did previously. We have to work with a more fluid model of escape because we have a bulk escape. And that's what we call the hydrodynamic escape. It's important to remember that the thermal escape really comes from the thermal energy that in itself comes principally from the EUV, XUV fluxes, except in some extreme environment. There's an important parameter that allows to see if we are in a Jeans escape or if we are in hydrodynamic escape, and it's the Jeans parameter. That critical parameter is basically the ratio of the gravitational energy to the thermal energy. So if we are above that parameter, the atmosphere is dominated by gravity and it's in slow escape. If we are under, it's dominated by the thermal energy and we are likely in hydrodynamic escape. It's important to realize that this critical parameter is different from atoms and molecules. It's 1.5 for atoms and 2.5 for molecules. So around the critical level, some direct simulate Monte Carlo models are needed to work. Hydrodynamic escape was extremely important for the early solar system. The early rocky planets like Earth, Mars, and Venus had hydrodynamic escape, and we believe that it is at the origin of most of the isotopic fractionation of the planet. Other processes led to more fractionation later, but in the origin, that is a big one. Thermal escape, we have seen, is very important for the early solar system, and is still a very important process right now for light species. However, it's important to know that thermal process is not the only source of escape, and we can have other sources that can become more important than thermal process even in the solar system right now, and it is non-thermal escape. What is non-thermal escape? Sometimes we cannot really consider particle distributions to be Maxwellian, but we can approximate those by a Maxwellian plus very high energetic particle distribution. And that's what we call suprothermal, this really energetic particle distribution. For example, extreme UV and XUV lines in the solar spectrum are non-thermal distribution. Auroral electrons are another example of non-thermal distribution. So we have processes that are discrete, that can leave atoms and molecules with energies well above the escape velocity, regardless of the local temperature. Those are non-thermal escape processes. They have different sources. For example, the photochemistry, the ion acceleration in fields, charge exchange, sputtering processes, and so on. One big escape processes is the photochemical escape, coming from electron impact dissociation, for example, or from ion recombination. At Mars, right now, one of the main escape processes is the dissociative recombination of the ion dioxygen, giving 2 oxygen above escape velocity, and this is one of the main sources of oxygen loss at Mars. We have ion escape, which can come in several cases, like the non-magnetized ion escape. For example, the charge exchange, we have the proton coming from the solar wind interacting with the neutral atmosphere, leading to particles from this atmosphere to escape. We have the bulk ion escape, so we have ionosphere interacting with the magnetic field of the solar wind and basically sweeping the ions away. We have processes like pickup and sputtering, when we have an ion creating from the neutral atmosphere and accelerated by the solar wind to escape, but that ion can be hitting the atmosphere back, release its energy by transferring it to the atoms in the atmosphere, leading to more escape. This is what we call the sputtering. In the case of a magnetized planet, We have charge exchange processes as well. For example, when a particle, when an ion is trapped in the magnetosphere of the Earth, it can interact with the neutral atmosphere, basically becoming an energetic neutral atom and escaping. This kind of charge exchange is actually the main source of hydrogen escape at Earth when we are in the conditions of low solar activity. In addition to that, we have the question of ionospheric outflow or polar wind, which is the main source of oxygen escape at Earth, and basically comes from the creation of electric field along the magnetic field line near the pole, and this electric field accelerates the ion, like the ion oxygen, up to escape speeds. In this figure, you can see a little summary of the different escape processes and some of the different conditions. For example, at the bottom right, you see some kind of escape at Mars. We have a little bit of magnetized escape at Mars near the crustal magnetic field. We have a lot of ion escape from the ion plume, some kind of bulk ion escape, and also the photochemical escape and the photodissociation at Mars. Bottom left, you have the case of Venus, which has a lot of ion pickup and the sputtering bulk ion escape. Top right, you have the case of the comet, which have a lot of escape that could be considered as hydrodynamic, but that also happens for our planet in the beginning of the solar system. And we have some charge exchange in unmagnetized conditions that make the comet lose a lot of molecules. And finally, top left, we have the Earth, which is losing some of its hydrogen through Jeans escape or through charge exchange magnetized, and finally losing some of its oxygen and other species through the polar wind near the poles. We have seen that the story of the solar system planet's atmosphere is very interesting. The solar system planets had a lot of escape, and in the history of the solar system, a lot of different escape processes happened. In the past, hydrodynamic escape was very important for the rocky planet, but now it has changed. We have now Jeans escape at all the planets in the solar system, but it can be dwarfed by other escape processes, like what is happening in Venus now, where the escape is dominated by non-thermal process. Earth has a lot of escape through the polar wind, but also through Jeans and charge exchange. Mars's escape is really changing a lot, and the solar activity can dramatically change how much particles are escaping its atmosphere. So it's important to try to study the story of the atmosphere. And one process can really help us here. It's the isotopic fractionation. But some paradoxes with isotopic fractionation still exist, and I can say that we need a little bit more measurements right now. One of those paradoxes is the xenon paradox. Basically, xenon is a very heavy atom, and we are discovering that the isotope are not fractionated at Earth, and the hydrodynamic escape cannot really explain that situation with xenon. So some solutions were based on escape of xenon have been proposed to try to see where it comes from. And considering that there is way less xenon than other species like krypton, it was proposed that we had way more escape through ion escape. And Zandler et al. 2019 proposed a mechanism for this. However, this process requires high diffusivity coefficient and a very specific thermosphere and can be really criticized here. However, When we look at all the xenon and all the process able to take away xenon from the atmosphere, we discover that organic hazes can trap some of that xenon in the mantle of the Earth, and there's a lot of xenon isotope exchange within the mantle. So maybe the escape is not the solution to that xenon paradox, and hopefully the measurements of the xenon at Venus will help us have a little bit more insight on this problem, and maybe show us that there is no xenon paradox because escape is not something that was important in the history of that species. After looking at the question of the different processes that leads to the escape of the atmosphere, it's important to look at the role of the stellar or solar activity and its change in time. A star has a lot of activity that can be really changing with time. We have the problem of the flare, of the coronal mass ejection, and the energetic particle event that have an influence on the heating and ionization at the planet, which then leads to thermal and non-thermal processes. It leads to have a higher stellar wind, which brings a lot of non-thermal escape. And we have also extremely energetic particle events, which have a little effect on the upper atmosphere and a lot of effects in the lower atmosphere. So it's important when we want to have a picture of the loss of atmosphere into space to look at the activity of the star. And we can see by looking at stellar analogs of the sun that that activity changes with time and is linked to the rotation of the star. In this figure from 2 et al. 2015, we are seeing the XUV and EUV fluxes, XUV on the left, EUV on the right, in function of the age, in millions of years, of a solar-like star. And you can see that we have a lot of variation in this fluxes. So let's look at the blue curve. It can be very high XUV flux, up to 10 to the power 30 in the early age of the sun, and goes down to 10 to the power of 27 arc per second for a more current sun. The question is, how did it evolve in between these two ages? Is it the blue curve or the red curve? And basically it's really changing in function of the rotation of the star. And you see, we are speaking about several orders of magnitude between these two conditions, and that really changed the whole history of the escape of an atmosphere. To better understand the escape and the condition around the stars where we have the potentiality of having an habitable planet, we need to observe these stars. So for the M dwarf, and more, let's be a little bit more general here, to the F to M stars, we would like to have a little bit more understanding and more observation of their activity, and that's why we proposed the ESCAPE mission with the PI Kevin France to try to better quantify this atmospheric loss rate. And this mission is currently being reviewed by NASA. Now that we have been speaking about the escape processes and we have been speaking about the activity of the star and its evolution with time, let's speak about the role of the magnetic field. As seen before, we have a problem with the magnetic field because a lot of people are saying that it will just shield the planet against escape to space. If a magnetic field were really shielding a planet without a magnetic field should not have any atmosphere. Look at that image taken from the High Node satellite. You see that little yellow line on the upper left border? Yes, it's Venus. And that little line, it's basically the refraction of the stellar light on the atmosphere of Venus. Venus has no magnetic field, but has a massive atmosphere. We can see that Mars has a remnant magnetic field and a faint atmosphere, and Mercury has a nice magnetic field and no atmosphere. So basically, the atmosphere, the problem of shielding of the atmosphere by the magnetic field, even if it really applies to the Earth where we have a big magnetic field and atmosphere, doesn't really apply everywhere. And when we speak about shielding, at best, it will be shielding some very specific atmosphere and very specific conditions. Let's go into more details. When we make measurements of the escape rate with satellites like MAVEN or Venus Express, we see that the Earth, Mars and Venus currently have similar escape rate. And when the MAVEN satellite goes above Martian crustal fields, it can see some enhanced or reduced ion escape depending upon the condition, day or night, of strong or low solar activity. When we go to the Earth, we see that the magnetic field prevents particles to reach low altitude. But actually, these particles go into high latitude, and we have increased the precipitation of particles at high latitude. And when we have this precipitation, we have an enhanced of the polar escape during high solar activity. So overall, the question is, on average, is it really protecting the atmospheric escape from these particles? And this is a less and less convincing observation. Some people have been thinking that if we look at the Earth when it had magnetic field inversion and therefore a lower magnetic field, it should probably have had enhanced escape. But there is nothing that indicates that there was an enhanced escape at the time. So basically, there is currently no decisive argument or whether or not the magnetic field protect or enhance atmospheric escape. What we can conclude from the observations that we have right now is that the magnetic field seems to protect from some escape processes while enhancing others. And the difference between magnetic field versus non-magnetic field is not big enough to shield a planet from the escape. We may have some 50% difference from the observation we have right now, but it's not 99% difference that would really make a big number in the creation, in the stability of an atmosphere. However, we can say that the question of the magnetic field shielding may be badly posed. It would be better to consider the atmospheric composition, the planet mass, the stellar activity, and then say how much escape does the presence of the magnetic field prevent or enhance in these conditions. As an example of how we can apply the magnetic field, let's see the problem of the Proxima b planet. And that was a case study that was published in Garcia Sage et al. 2017. The simulation of Proxima Centauri b was done using the polar wind outflow model by Grosser et al. And we basically swapped the Earth, the current Earth, with Proxima Centauri b in the model. And we had to do some little approximations here and make some hypotheses about the exospheric temperature to see what's going to happen. So let's put our Earth with its own magnetic field around Proxima Centauri b, and let's look at how much oxygen it's going to lose. Let's look at how long we will lose an ocean's worth of oxygen with the Earth at Proxima Centauri b. In this figure, you are seeing on the right the lost time of an Earth in gigayear. The different lines correspond to the different thermospheric temperature of the planet, and in the x-axis you look at basically the opening of the magnetic field line of the planet in function of the pressure by the solar wind. So the more you have pressure from the solar wind, the more you are opening the magnetic field, and you have open magnetic field lines down and down in latitude. Let's consider a 55-degree opening, which is not something totally crazy when you consider the conditions at Proxima Centauri b. And let's look at the different lines. The blue line is if we have one exospheric temperature at Earth, and the yellow line is if you have 4 times. And basically, it means that for 2 exospheric temperature of the Earth, you will lose that ocean's worth of atmosphere in a couple of gigayear, and if you have 3 or more, you will lose the ocean in less than a gigayear. 2 or 3 exospheric temperature for Earth-like planet at Proxima Centauri b is really something small with respect to the EUV conditions that we have over there. So basically what this calculation shows is that there is no really any magnetic protection around the Proxima b with a Earth-like planet. And it shows that basically we can really lose a lot of atmosphere even with a magnetic field. So we have seen that the escape is something extremely important to understand the origin, evolution, and the habitability of the atmosphere. We have seen that the red dwarf have their habitable zone really affected by the star and may have problems having an atmosphere. Fortunately, if there is a lot of outgassing, that is something they can survive a little bit longer. We have seen that we need to study the stellar wind around the star to better understand what is going on with them. And we have seen that it is important to address the activity of the stars to study the habitability of its planet. I have also a presentation where I show that it's, in addition, very interesting to study the activity of the stars for its effect in the lower layers of the atmosphere, where it can actually affect the chemistry and the biochemistry a little bit more. Future work with respect to the question of the atmospheric escape includes the creation of generalized escape codes that allow us to take into account several escape processors in 3 dimensions with the effect of all the different particles. And we are working on part of that code with the calculation of polar wind outflow for non-magnetized planets such as Venus. We have a paper on the review paper on the escape processes that was published last year in the Journal of Geophysical Research.
Thank you for watching. In this series of videos, we have been seeing how we created an habitable world. In the talk of Vardan Adibekian, we have seen how the composition of the star and the composition of the planet are linked. Thanks to observation and statistical studies, he has been showing us how this link is actually visible in the data. This link is not coming from nowhere. When the star forms and the planet forms, they have a disk, an accretion disk, and the signature of the composition is seen both in this disk and in the star. After that, Natalie Hinkel did show us how we can look at the composition of the planet and link it with the possibility of having some biochemistry happening on it. She allowed us to see the link between the composition, the biochemistry, and the geochemistry. All these things are extremely important because without that chemistry, it's impossible to have habitability and impossible to have life. Finally, in my talk, I, Guillaume Gronoff, did show how we have to link the planetary composition with the escape of gases into space to be able to have an habitable atmosphere. Because without an atmosphere, the conditions for habitability are very dire, and we are probably unsure to be able to observe whether or not a planet is habitable. I will try to do an overall conclusion to this series of talk, saying that we have seen how the evolution of a star, of a planet, and of the planetary atmosphere is really linked to the habitability and to the possibility to observe and determine that this planet is habitable. Thank you for watching, and if you have any question, don't hesitate to contact us. Thank you.